Today we are going to look at directional derivatives and the gradient vector. Just another application of all those partials that you found some time ago. So first of all, I will start with directional derivatives. What are they? Another word for the directional derivative of a function of several variables is the rate of change of the function. So just know directional derivatives is the same as rates of change. So let me explain that. Remember, we're going to look here. I'll give you an example where we look at a function of two variables, which means we're in 3D, right? So it's a different thing than when we were in 2D. When you were finding rates of change or slopes, that was completely different. So let's look at it in 3D. So imagine that you are on a mountain. Okay, so you're in 3D, you're on a mountain. And let's just say that the function f is the height of the mountain range, right? If you want to calculate, let's say you're standing anywhere and you want to calculate the slope of the ground in front of you. It depends on which direction you're facing, right? Okay, if you're facing in the front, you'll have a different slope. Facing on the side, you'll have a different slope. So the slope, what I'm saying is that the slope of the ground in front of you depends on the direction that you are facing. The slope of the ground in front of you is called the directional derivative. The slope of the ground in front of you is said to be the rate of change of f in that direction, in this particular direction. This is why it's called a directional derivative. Now, I think the last time when we looked at the partial of f with respect to x and the partial of f with respect to y, I told you they were rates of change or they were slopes in the x and the y direction. So actually, these first partials are examples of directional derivatives. So that should tell you that there are an infinite number of directional derivatives, right? Because they all depend on a direction. So how are we going to compute the directional derivative, the rates of change? We need a direction, right? Good. So the first thing you do, you specify a direction. Now, let us say you are standing and then in the direction of the vector 2, 3, right? Now remember, the vector 2, 3, there are many other vectors in that direction that you can specify. For example, any multiple of 2, 3 is a possible direction, right? So 2, 3, 4, 6, 6, 9, these are all the same direction. Okay, so to be uniform, to be consistent, we specify the direction by taking the unit vector that points in the direction in which you want to compute the slope. So you always take the unit vector, right? And remember how you find the unit vector? We did that earlier on, right at the beginning of this course. How do you find the unit vector in the same direction as another vector? You divide that vector by its length. Remember that. Okay, so that's what we're going to do. All right, so now let us look at the definition of the directional derivative. The directional derivative of f at the point AB and is denoted by this du. So u is the unit vector pointing in the same direction in which you want to compute the rate of change. F of AB, or sometimes you might see this direction, f sub u of AB, and is defined by this. So it's the dot product of two vectors. What are the two vectors? The first vector would be the partials, the first partials at that point. The second vector would be the unit vector in the direction in which you want to compute the slope. And so you find the dot product. And of course, this can be extended to 3 variables. So this should be, I need a third coordinate there. Let me go down a bit here. So the directional derivative of f at ABC, because it's 3 variables, right? So you need a third coordinate there. Again, is the partials at the point. So these partials here must be computed at the point A, B, C, and of course dot it with the unit vector. Now remember when we did dot product, you always get a number, scalar. Directional derivative is not a vector, it is a number, it is a rate of change, okay? So if you get a vector, you know you're wrong. It has to be a number. So that is the definition. So now let's do some computing. Find the directional derivative of the function f of xy equals x cubed y to the 4th at plus x to the 4th y cubed at the point 1, 1 in the direction indicated by the angle pi over 6. Okay, so the first thing we can do, let's find the partials at the point. Okay, so find the first partial, fx, and that is equal to 3x squared y to the 4th plus 4x cubed y cubed. And then right away you can find that partial at the point 1, 1 by just substituting. So that would be 3 plus 4, which is 7. Partial with respect to y now, that is 4x cubed y cubed plus 3x to the 4th y squared. At 1, 1, that partial is again 7. Okay? What did I switch something here? You good? Okay, so we find the first partial. Now we need to find the direction, right? So what did it say? In the direction indicated by this angle. Now it's quite easy to find that direction, but let me draw a figure so you can see how to do it. Alright, so we go in here. So we want pi over 6 here. So this is the vector that we want. Okay, and we need the components of that vector. Remember, that vector has to be a unit vector. So in other words, the length of that line must be 1. Okay, so if we draw a right angle triangle here, we should be able to get the coordinates of this point, right? This here, if you remember your trigonometry, this distance over 1 is cosine pi over 6. So therefore this distance here is simply cosine pi over 6. And this distance here is simply sine pi over 6. So therefore the vector u, it's already a unit vector, is made up of cosine pi over 6 sine pi over 6. Okay, and that's always what it is. When you have, it's quite easy. When you have specified the actual angle, the unit vector is always cosine of the angle, sine of the angle. Always. Alright, so now let's find the directional derivative. Any questions so far? So the directional derivative at u of f at 1, 1 is equal to, find the dot product of the partials. So we got 7, 7 dot the unit vector cosine pi over 6 sine pi over 6. And you just work that out. So the dot product, that is 7 cosine pi over 6 plus 7 sine pi over 6. Cosine pi over 6 is root 3 over 2. So that's 7 square root 3 over 2. Sine pi over 6 is a half, 7 over 2. And that leaves us with 7 times square root 3 plus 1 over 2. And that's it. Leave your answer in terms of radicals, okay? Don't round it off. Let's be as accurate as possible. So that's the first one. Any questions? Okay, let's do another example. Find the directional derivative of f of xy equals e to the x sine y at the point 0 pi over 3 in the direction of the vector v specified by negative 6, 8. So the first step, let us find the partials. So let's find the partial of f with respect to x. And that's the same thing because the derivative of e to the x is the same thing. And then let's find that partial at the point right away, 0 pi over 3. So we substitute. You get e to the 0 sine pi over 3, which ends up being square root of 3 over 2. Partial with respect to y equals e to the x cosine y. Let's find this partial at the same point. So that is e to the 0 cosine pi over 3, which ends up being 1/2. Good. So we have the partials at that point. The next thing we need to find is the direction. Now, if you look at this vector v, it is not a unit vector, right? So you would need to find the length of it and divide the vector by its length to find the unit vector. So the length of v, do that first, equals the square root of negative 6 squared plus 8 squared, which ends up being 10. So let us find the unit vector in the direction of v. So the unit vector u, we're going to divide the components of v by 10. Negative 6 over 10, 8 over 10. And you can reduce that, negative 3/5, 4/5. Any questions so far? So now let's find the directional derivative. So our notation, d sub u of f at the point 0 pi over 3. So we take the dot product of the two vectors. The first vector would be the partials, square root 3 over 2 1/2, dot the unit vector, negative 3/5, 4/5, and let's work that out. So that is negative 3 square root 3 over 10 plus 4 over 10. And you're done. That is, you can just put it as negative 3 square root 3 plus 4 all over 10. Any questions on these two? So the two steps: find the vector of the partials at the point, find the unit vector in the direction, and find the dot product, and you get your directional derivative. Okay, so I think you have two of them to do. Try these, please. 3 and 4. Okay, let's go over it. So number 3, the partials. Partial with respect to x equals minus y e to the minus x. So be careful, it has to be minus because the coefficient of x is minus. Fx at 0, 4 ends up being minus 4. Partial with respect to y is just e to the minus x. Fy at the point is simply 1. The unit vector is simply cosine 2 pi over 3 sine 2 pi over 3. And if you work that out right away, you'll get minus a half square root 3 over 2. You don't need to though. And so the directional derivative of f at the point 0, 4 is the dot product of negative a half square root 3 over 2 with negative 4, 1, which works out to be 2 plus square root 3 over 2. Or you can put this as 4 plus square root 3 all over 2. Any questions with number 3? Number 4. Partial with respect to x equals 4x cubed minus 2xy cubed at the point 2, 1, and you will get 28. Partial with respect to y is minus 3x squared y squared. At the point 2, 1, you'll end up with minus 12. The unit vector in the direction of v, so the length of v is the square root of 1 plus 9, which is square root 10. And so u is the vector 1 over, I'm going to use angle brackets, I prefer it like that. And so the directional derivative of f at the point 2, 1 dot product 28 negative 12 with 1 over square root 10, 3 over square root 10, oops, which works out to be negative 8 over square root 10. Any questions on that? Okay. Let's move on. So that was directional derivative. Let's move on to the gradient. The gradient vector. Let f be a function of two variables. The gradient of f denoted by this symbol, and you read it as del f, is given by del f is simply the vector with the partials, the first partials. Okay? For a function of three variables, del f again would be the vector with the three partials. So note, gradient is a vector. Directional derivative is a constant, a scalar. So by the way, another way of writing the directional derivative is therefore the dot product of the gradient with the unit vector. So that's an easy way to learn it. Okay, so let's do some questions whereby we find a gradient. So A says find the gradient of f, B is the gradient of f. I'm not sure where that A came from. Find the gradient of f at the point P. So now in number 1 I gave you the function, the point, and I also gave you a unit vector. So maybe we can also find the directional derivative. just for practice, maybe we'll just do it with one of them. Okay? Alright, so let's find the gradient of f, then the gradient at the point P. So part A, the gradient is just made up of partials. So the first partial with respect to x, 2xyz minus yz cubed. Now, you know, right away, let's find this at the point P. We have to do it anyway, so let's just find it. So substitute these coordinates for x, y, and z. We get 2 2s of 4, so that's a minus 4, and that's a plus 1, which is minus 3. Partial with respect to y now, and that is x squared z minus xz cubed. Partial with respect to y at P is equal to, so that's 2 squared, that's a 4, minus x 2 times, so that's a 2, and that gives us 2. And finally, partial with respect to z is x squared y minus 3xyz squared at the point P is, so x squared y, that's minus 4, minus 3, that's 3 2s are 6, times minus 1, that's a minus, okay, so that's a plus 6, and this is 2. So part A is asking you, let me take out A, I'll just put A down here now. So A is asking you for del F, so you just put all the partials as a vector, so that's 2xyz minus yz cubed, comma, x squared z minus xz cubed, comma, x squared y minus 3xyz squared. And then B, the gradient at the point P, so del F at P is just minus 3, 2, 2. Okay? So if I'd given you a question like this, and I asked you to find the gradient, then find the gradient at the point P, and then I asked you find the directional derivative, it would be quite easy, because the directional derivative, note, the directional derivative of u in the direction of u of f at P is exactly the gradient negative 3, 2, 2 dot the unit vector. It's already a unit vector, so 0, 4/5 minus 3/5. All right? And when you work that out, you get 8/5 minus 6/5, which is 2/5. Okay? Let's do another one. Number 2. Okay, so let's find the gradient. So the partials, let's do it. So the partial with respect to x, again we need to use the chain rule there. So that's 2 cosine 2x plus 3y. Find the partial at the point P. So that is 2 cosine 2x, that's negative 12 plus 3y12. So that's 2 cosine 0. Cosine 0 is 1, so that's 2. Partial with respect to y is 3 cosine 2x plus 3y. At p is 3 cosine 0, which is 3. Any questions so far? So A del f is simply 2 cosine 2x plus 3y, 3 cosine 2x plus 3y, and B del f at p is simply 2, 3. Let's go ahead and calculate the directional derivative in the direction of that vector u, which is already a unit vector. So we don't have to find it. So I'll say note the directional derivative in the direction of u of f at p is the gradient 2, 3 dot this unit vector. Square root 3 over 2 minus 1 over 2. Let's work that out. That's square root 3 minus 3 halves. Any questions? So that's the gradient. We're going to do more questions on the gradient and the directional derivative in a little while. But I need you to understand the significance of the gradient, because we've just been calculating stuff, right? I told you what the directional derivative was. It's the slope, right? The rates of change of a function in any direction. So that's okay. But what exactly is a gradient? What does it mean? What is its significance? So let's look at that. You can look at the gradient in a number of ways. Its definition is that it is actually the derivative. So when somebody tells you what is the derivative of a multivariable function, it is actually the gradient, right? So that's another way of looking at it. Remember that the gradient is a vector, right? But what exactly is that vector? What does it point to? That is the significance of it. Okay, let's move on to other properties of the gradient. The gradient at a point P is orthogonal to a surface at the point P. That's a very, very important point. Let me just illustrate it. So let's say I'm going to draw a surface, but remember, an easier way to draw a surface is to use level curves, right? Because that's a surface, a three-dimensional surface as a two-dimensional, right? So let us say these are the level curves, right, of the function z equals f of xy. And let us say that is the point P, right? The gradient is orthogonal to that surface. So it's orthogonal, it's a right angle. So this is del f, right? It's orthogonal, 90-degree angle. Now here is the significance of the gradient. The gradient specifies the direction to move to increase a function. In other words, it points in the direction of the greatest increase of a function. This is very important. The gradient points in the direction of the greatest increase of a function. Let me explain what I mean by that. I'm going to do a little example here. So I have an oven. Let me draw my oven, okay? This is an oven. It's a special oven, so I'm going to call it Delia's oven. And I want to bake a cookie in there. All right. Now my function is going to be, f of xy is going to be the temperature in that oven at a point, right? So f of xy is going to be my temperature in the oven at the point xy. So I want to bake my cookie, and I want to put it at a spot in the oven where it will cook the fastest. I want to put it, therefore, at the point where the temperature is the greatest. I don't want it to burn, you know, but that's where I want it to go. I want it to go at the place where the temperature is at a max. What do? I use my gradient. So I take my cookie, is a little dot here, right? And I calculate the gradient. So I just put it at a random location, anywhere. I really don't care where it is. Put it anywhere and calculate the gradient, okay? So I calculate del f at the point, right? So del f at the point, and then I move my cookie in that direction. So this is where my cookie is now. Now at this new point, I calculate the gradient again. Del f at the point, and I move my cookie in this direction. I do that. I continue doing that until I reach the hottest temperature. What's wrong with this? And lo and behold, this would be my maximum temperature. How do I know I have reached the maximum temperature? If I calculate the gradient at this point, what do you think I will get? 0. Right. So I know I have reached. So that is the significance of the gradient. It points in the direction of the greatest increase of a function. So by the way, when you are at this maximum location, there is no longer any direction of greatest increase. There is now a direction of greatest decrease. Right? So I would go in the opposite direction of the gradient to find the direction of the greatest decrease. All right? Okay, we'll look at some other points and then we'll do some examples. Recall, what is the directional derivative? It is the rate of change of f in all possible directions. Now tell me, if you understand what I just said, this is my question. In which of these directions does f change the fastest? In the direction of which vector? In the? I'm not hearing you. No, it can't be the horizontal direction. It's the direction of the gradient. Remember, the gradient points in the direction of the greatest increase. Right? The greatest increase is where the function changes faster. So, in the direction of del f. Another question. What is the maximum rate of change and in which direction does it occur? Now, I need to give you a theorem for that, and I'll explain this in a little while. the maximum value, so in other words, my question is, what is the maximum rate of change? In other words, what is the maximum directional derivative? Remember, rate of change is directional derivative. What is the maximum directional derivative? The maximum value of the directional derivative is the length of the gradient, and it occurs in the direction of the gradient. Now, the latter part should make sense to you because we're looking at maximum rate of change, right? So it occurs in the direction of the gradient. But why is the maximum value equal to the length of the gradient? Let me show you why. Recall, what is the definition of the directional derivative? It is the dot product of the gradient and the vector u, right? Go back to your definition of dot product. The dot product is equal to, remember, you can write, let me put it another way. You can use your dot product to find angle between two vectors, right? That's what we did. And we said that dot product is equal to the length, the product of the length of each vector. So this times the length of u cosine the angle. That's what we did really early on, right? Okay, now let's see the maximum. We want the maximum of the directional derivative. So, this cosine theta, what is the maximum value of cosine? 1. What is the length of u? What is the length of a unit vector? 1. So therefore the maximum occurs, so when you multiply 1 by 1 is 1, so the maximum of the directional derivative is just the length of the gradient. Very, very important point. Okay, let's look at some questions. So again, the maximum rate of change is the length of the gradient, and the direction in which it occurs is actually the gradient. The gradient points to the maximum, points to the direction of, in the direction of greatest increase. Okay, so let's do number 1. Find the maximum rate of change of the function 4y square root x at the point 4, 1 and the direction in which it occurs. Okay, so let's write f of xy as 4y x to the half, okay, so that we can find the partials. So let's find the first partials, and we are going to find the first partials at the point 4, 1. So the partial with respect to x, a half times 4, that's 2y x to the minus a half, which is 2y over square root x, and the partial of f, the partial with respect to x at 4, 1 is 2 over square root 4, which is 1. Partial with respect to y is simply 4x to the half, and at 4, 1, this is 4 times square root 4, which is 8. So the gradient at 4, 1 is the vector 1, 8. So the maximum rate of change is therefore rate of change is the length of this vector 1, 8 and that is equal to the square root of 1 plus 64, which is square root of 65, and it occurs in the direction of the gradient, in the direction of 1/8. Okay? Any questions? Okay, try this one on your own, please. Okay, let's do it. So the partial of f with respect to x is y cosine xy. At the point 1, 0, we get 0. Partial with respect to y is x cosine xy. At the point 1, 0, you get 1. So the gradient at 1, 0 is 0, 1. And so the maximum rate of change is the length of the vector 0, 1, which is 1. And it occurs in the direction of 0, 1. Any questions? Okay, let's move on. We're going to do some applications now. Let's bring it all together. Suppose that over a certain region of space, the electrical potential V is given by V of xyz equals 5x squared minus 3xy. Oh, that's not an equal sign there. That should be a plus, xyz, plus. Oops. A. Find the rate of change of the potential at the point P345 in the direction of the vector V equals I plus J minus K. B. In which direction does V change most rapidly at P? C. What is the maximum rate of change at P? Okay, so we have a number of things to do here. So part A is asking you for the rate of change of the potential. In other words, what is the rate of change? What are you asked to calculate? Another word for rate of change. Directional derivative. Okay? So we want to find the directional derivative, which is the dot product of the gradient and the unit vector, right? So let us find the gradient. So find V partial with respect to x. That's 10x minus 3y plus yz. Find this partial at the point P345. So that's 30 minus 12 plus 20, which is equal to 38. Partial with respect to y now is minus 3x plus xz. At the point P equals minus 9 plus 15, which is 6. With respect to z, it's simply xy. At the point P, it is 12. So therefore, the gradient of V at P is the vector 38, 6, 12. So that's the first thing. Now, what else do we need to find in order to find the directional derivative? What should we do now? Find the unit vector. So in order to find the unit vector, what should we find first? The length of v. So the length of the vector v is the square root of 1 plus 1 plus 1, which is square root 3. And so the unit vector is equal to, again, I'm going to use angle brackets instead of I, J, and K. That's just my preference. 1 over square root 3, 1 over square root 3, minus 1 over square root 3. And so we are ready to find the rate of change, which is the directional derivative. So the rate of change is equal to duv at P, which is the dot product of the gradient 38, 6, 12 with the unit vector 1 over square root 3, 1 over square root 3 minus 1 over square root 3. And you work that out. So that is 38 plus 6 minus 12 over square root 3, which is equal to 32 over square root 3. So that's A. B. In which direction does F change most rapidly at P? What would that be?
38, 6, 12.
The gradient. Beautiful. So B is just a gradient. 38, 6, 12. That's all. Just write it. Finally, what is C? The maximum rate of change at P. So we just did that. The maximum rate of change is the length of the gradient. Maximum rate of change is the length of 38, 6, 12, which is square root of 38 squared plus 6 squared plus 12 squared, which is, I can't understand my handwriting, which is, okay, you need to help me. What is all of this squared? 40.3. Give it to me exact. Square root of what? 2. Oh. 2 square root 406. Yes. Okay. Yes, that looks familiar. Right. So that's the first one. Any questions on that? Okay. The next application. So there are different parts. This one is a little bit more challenging. Okay, number 2. A metal plate is placed on the XY plane in such a way that the temperature T in degrees Celsius at any point P is inversely proportional to the distance of P from the origin. Suppose the temperature of the plate at the point -34 equals 50 degrees. Find an expression for T. Now this one is a little bit more challenging because you were not given the function, right? You are asked to find the function. So let's find the function. So that's what makes this challenging. You have to go back to algebra. You were told that the temperature is inversely proportional to the distance of P from the origin. Now the first thing we need to find, what is the distance of a point from the origin, right? So P is the point XY. So let's find the distance. So the distance of P from the origin equals, so remember how to find the distance between 2 points? Square root of x minus 0 squared, which is x squared, plus y squared. So that's the distance. All right, now let us go back to your college algebra to find the expression for t. You were told that t is proportional to or inversely proportional to the distance, right? If you remember inverse proportion, t is equal to k, the constant, over the distance. Now you need to find k. And how can you find k? By using the information in the question. Look at the last line. The temperature at the point -34 equals 50. So in other words, when t is 50, x is -3 and y is 4. So substitute that and that will give you k. So that's k over the square root of 9 plus 16. 50 is equal to k over 5. So k is 250. And so this is our function. So t of xy is therefore 250 over the square root of x squared plus y squared. So I think that was the most difficult part of this question, finding that expression. Okay, any questions before we continue?
Do we have one like that on test?
I could give you anything like that on a test. Let's.
Yes, definitely yes.
Can I give? Say that again.
Can you get one like that on the test?
Can you get one like that on the test? Anything is possible. Why not? Especially as I did it already. Why not? B.
Your plugs coming loose again.
B. Thank you. Find the gradient of t at the point -3, 4. So you know we have to find the partials, right? Now let's rewrite that function using exponents. So t of xy is equal to 250 times x squared plus y squared to the half. Okay, it's easier to do it that way. Now let's find the gradient, so let's find the partials. T with respect to x.
You did -1/2.
Negative, thank you very much. Very good. T with respect to x, that's -1/2 times 215, -125 times x squared plus y squared to the -3/2 times 2x, chain rule. So this is equal to -250x over x squared plus y squared to the 3/2. Now right away let's find tx at the point -3, 4, which is -750 over 9 plus 16 to the 3/2.
Is it positive 750?
Positive 750, thank you. And this works out to be 750 over square root of 25 is 5. 5 cubed is 125, which is 6, is it? Now with respect to y, so again that's -125 times x squared plus y squared to the minus 3/2 times 2y, which is minus 250y over x squared plus y squared to the 3/2 at negative 3, 4. That is negative 1000 over 125, which is minus 8. So the gradient del t at negative 3, 4 is the vector 6 minus 8. That's B. C. In what direction does the temperature increase most rapidly? Tell me.
6 negative.
Gradient. Very good. You're getting the hang of this. 6 negative 8. Nice. Next one. In what direction does the temperature decrease most rapidly? Negative 6, 8. In the opposite direction. Isn't this lovely? Negative 6, 8. Opposite direction. Fantastic. Now I absolutely love this question. In what directions does the rate of change of t at the point equal to 0? It's what? I'm not understanding. No, they asked for in what direction. Listen again. In what direction does the rate of change of t equal 0? In what direction? It has to be in an orthogonal direction. Remember, let me just look at that. That's a beautiful question, huh? What is it? The gradient? The rate of change. The rate of change of V is equal to 0. So you want to know in what direction. What is rate of change? Rate of change is gradient, right, times the vector. Good? So in other words, you want to find a vector orthogonal to the gradient. A vector such that when you find the dot product of the gradient, you get 0. There are a number of vectors. Give me an example. Give me, where's the gradient? What did we get for the gradient again? 6 negative 8. Give me a vector, anybody, such that when you dot it with this vector, you get 0. Give me one, a possible one. Don't give me 0, 0. That's nothing. We're not going anywhere, right? So, negative what? Negative 8. And which? And what? 6. There are so many of them, but that's just one. That will do it, right? No, negative 6. Very good. When you dot product, you get 0. So that's just one, right? There are many. Good. So that's another way of phrasing that. That's the direction of no change, right? That's the direction where the temperature is constant. That could be phrased a number of ways. Okay. Any questions on this one? Okay, you have one application to do. Your turn. Same thing. Okay, so let's go over it. So A is asking you for the directional derivative. Did you distribute this or did you leave it as is? It doesn't matter. You distributed? Okay, let's distribute it. Doesn't matter to me though. So that's e to the x sine x plus e to the x sine y partial with respect to x, so you have to treat that as a product rule. E to the x sine x plus e to the x cosine x at 0, 0, that is 1. Partial with respect to y is e to the x cosine y with at 0, 0, that is 1. So the gradient at 0, 0 is 1, 1. Now we need to find the unit vector in this direction. So if I say that this is the vector v, 3, negative 4, its length is square root of 9 plus 16, which is 5. And so the unit vector is 3/5 minus 4/5. And so the rate of change or the directional derivative, oops, wrong, the notation, t at the point 0, 0 is 1, 1 dotted with 3/5 minus 4/5, which is negative 1/5. That's the rate of change.
Wait, Professor. It
Yes?
doesn't change the answer, but unlike the t with respect to x, isn't there supposed to be a plus e to the x sine y?
Plus e to the x sine y. You're looking at which one?
The t with respect to x.
T with respect to x. Oh yes, I forgot
But
that.
it doesn't change it. So.
Yes, I forgot to partially differentiate e to the x sine y, so I'm missing an e to the x sine y. Thank you. At what direction is the temperature increasing most rapidly? That's the gradient. In what direction is it decreasing most rapidly? Opposite direction to the gradient. In what direction does the temperature remain the same? That is where the directional derivative is 0. So you can either give me 1, negative 1, or any multiple of that. Any questions? So before we move on, let me see if you understand that. If you're climbing a mountain, f of xy is the height of the mountain above sea level, and you want to take the steepest route. What direction are you going? I want to go in the direction, I want to take the steepest route up the mountain. The direction of the gradient. Okay? All right. Any questions? Because we're moving on. That's directional derivatives and gradients. Okay, so this is a little lighter now. Tangent plane to a surface. So this time we're looking at a function of 3 variables now. And this is the equation for a tangent plane to the surface at the point ABC, and that is the function, that is the formula. So you have to find again the partials at the point, the first partials at the point. So let's do some examples. Find the equation of the tangent plane to the surface x squared plus y squared over 4 plus z squared over 9 equals 3 at the point P 1, 2, 3. Now to find the function x, y, z, that equation there for the surface, it must be equal to 0. So you'd have to subtract 3 from both sides. So therefore, your function f of x, y, z is going to be x squared plus y squared over 4 plus z squared over 9 minus 3. Okay? And now, you're going to do the same thing we've been doing all along. Nothing new. Let's find the partials at the point. Partial with respect to x is 2x. At the point P, 2. partial with respect to y is a half y. At the point P is 1. Partial with respect to z is 2z over 9. At the point P is 6 over 9 or 2/3. Any questions? Okay, so let's find the equation. The equation, it's partial with respect to x2 times x minus the x coordinate of P plus 1 times y minus the y coordinate 2 plus 2/3 times z minus 3 equals 0, and you just simplify. Now that should look really, doesn't that look familiar to you? You did that some time ago when you were doing vectors, right? And you found these, the 2, 1 and 2/3 was the normal. Remember that? The normal to the plane. Okay, so, or to the surface. Let's do this now. What's that? 2x minus 2 plus y minus 2 plus 2/3 z minus 2 is 0. What's that? 2x plus y plus 2/3 z equals 6. Okay. So I hope you're recognizing why we had to do vectors first. It's just coming up. Let's do this one. Find the equation for the tangent plane to this surface at the point P 335. Okay, so again, let's write the function f of x, y, z. So that's 2 times x minus 2 squared plus y minus 1 squared plus z minus 3 squared minus 10. Okay, who would like to give me the partial with respect to x here? 4 times x minus 2, great. What is this mark here? And what is that partial at the point P? Anybody? 4. Somebody else give me the partial with respect to y. 2 times y minus 1. And what is that at P? 4. Again. Somebody else give me the partial with respect to z. 2 times z minus 3. And what is this at P? 10? 4. Oh, we have 3 4s. Interesting. Okay. Z is 5. Don't forget that. Okay, let's find the equation. So that's 4 times x minus 3 plus 4 times y minus 3 plus 4 times z minus 5 is 0. Okay. Four x minus 12 plus 4y minus 12 plus 4z minus 20 is 0. 4x plus 4y plus 4z equals 44. So x plus y plus z equals 11. So before, you were able to do this when the surface was a plane. Remember that? So you have to find the normal to the plane, right? And find the equation of the and look at what you're doing now to a surface, right? So it's coming together. Okay, it's your turn, I think.
No. Didn't say so.
That's number 3. Is it your turn?
It didn't say do.
It didn't say do, but I meant to say do. So I am going to put do.
Oh, there it is.
Here you go. Do it. So I have to say do all the time. It's your turn. I don't believe this. Okay, let's go over that. So f of x, y, z is x squared plus y squared minus z squared minus 24. Partial with respect to x is 2x. At the point P, it's 6. Partial with respect to y is 2y. At the point P is minus 8. Partial with respect to z is minus 2z. At the point P, it's minus 2. The equation 6 times x minus 3 minus 8 times y plus 4 minus 2 times z minus 1 is 0. 6x minus 18 minus 8y minus 32 minus 2z plus 2 is 0. 6x minus 8y minus 2z is equal to, what's that?
48.
48?
Yep.
And you can simplify that. 3x minus 4y minus z is 24. Any questions?